And in general relativity, this particular set of equations are the geodesic equations, because the theory is based on the axiom of the equivalence principle that effectively when you have a space-time, everything just follows straight lines, follows geodesics in that space-time. And when we try to test general relativity, we have to ask ourselves, which of those two ingredients are we testing? There is a wide range of experiments that test the equivalence principle. This was the idea that actually gave rise to all of general relativity to Einstein. But most of the things that you normally hear about when you hear about tests of general relativity assume that the equivalence principle is correct and testing the other half, the Einstein's field equation. The equations that allow us to describe how much does a particular object curve the space-time. And there are two reasons why we prefer to test that equation. One is, first of all, because Einstein kind of derived it by reverse engineering. He didn't have any bright idea. He just made up an equation that agrees with the data and gave the correct Newtonian limit. But that was 100 years ago. In the intervening 100 years, a number of really powerful theorems were proven that actually connect that aspect of the theory to fundamental properties of the physical universe. And one of them is the theorem by Lovelock that says, if you want to write any theory of gravity that lives in a normal universe, 3+1 dimensions, no brane worlds, no string theory, that is local, that is second order, like any theory of physics, and it involves only the metric, no additional fields, this is all the gravity, then general relativity is unique. If you make those four assumptions, you're uniquely led with the equivalence principle, led to general relativity. And what that means is that if we find any evidence anywhere in the universe that the predictions of that general, the GR field equations actually need to be modified, that automatically tells us that one of those four assumptions is not valid. That automatically tells us this is not tweaking the theory and adding an extra term. This kind of a measurement automatically tells us that one of those basic fundamental aspects of the physical universe is not correct. And this is really important. Of course, just by having a theorem like that is also a recipe how to modify gravity. You just have to modify one of those four ingredients and just turn the crank. And you can go to higher dimensions, more than 3+1. You can make it non-local. You can make it higher than second order. You can add scalar fields, vector fields, tensor fields, whatever you want. And every time you crank the tools of field theory, and then you derive a new gravitational theory. And just like every time you have a successful recipe, there's going to be many, many cooks making a lot of bread. Over the last 30, 40 years, there was a quite wide breadth of modifications to general relativity that were proposed based on these modifications. And a former student Tessa Baker, a few years ago, tried to organize them in this context. And this is what she did. So I don't want to show you because I want to point to any one of those particular theories. I just want to point out, and this is, by the way, 5 years old, that there is really a zoo of modifications that one can write based on this particular recipe, modifying Lovelock's theorem, that gives rise to a very broad range of modifications. And each one of those modifications makes a very broad range of predictions. So one thing that you can do is you can go one by one through all of those theories, calculate what are the implications of each of those theories for experiments, and compare it to experiments. And of course, not all of those theories will have visible implications for all gravitational experiments. But this is not very useful because, most likely people will be creating new theories and new modifications faster than people can actually calculate for all those modifications what the implications for all the experiments are. What we really want to do is we want to go at a different level of abstraction and ask ourselves what what content, what aspect of the theory of general relativity or the theory of gravity does its experiment actually probe. So this is the approach we're going to do. We're not going to go from let's modify gravity and see if it agrees with the data, but we're going to the data and ask ourselves, what do the data tells us about gravity. And the very first thing that you want to look at is what kind of gravitational fields are different tests probe, are different tests have access to. And this is something that we did again 4 years ago, where we took all objects in the universe, all astrophysical settings in the universe, and we plot them in what we call the gravitational field parameter space. The x-axis is the potential of gravitational field. This is your Newtonian potential in units of c squared. So anything to the right of that red line is effectively behind the horizon of a black hole. You cannot see it. And the y-axis is the curvature. This is the fundamental quantity of general relativity probed by the gravitational field. And it's not dimensionless because the theory has no scale. So it's in some CGS units, it doesn't matter what units that you're using. The sun is in the intersection of those two lines. This is the main sequence. And effectively tells you that whatever you do with the sun probes gravitational fields of this potential 10 to the minus 6 and this curvature 10 to the minus 27 inverse centimeter squared. You can plot here in blue all the fields probed by all the solar system objects, satellites around the Earth, white dwarfs, neutron stars and stellar mass black hole, really high curvature, supermassive black holes, the S stars that are in orbit around Sagittarius A star, the black hole in the center of the Milky Way. And if you go to the smallest possible curvatures, this is where cosmology comes in. These are rotation curves of galaxies, the blue curves. The red dots are the CMB peaks. And the green dots, the red dots are the density profiles of clusters of galaxies where we do dark matter experiments. And down here, this horizontal line is the curvature that corresponds to the dark energy, the omega lambda. This is the accelerated expansion of the universe. This is everything that we have in astrophysics. If we're going to find a modification to general relativity, it is going to be somewhere here. Of course, the theory might be modified in completely different scales. The Planck scales is, in the next floor above me, all the way to really high curvatures, but we do not have any way to do it experimentally. Instead, what we do is we look at the solar system. So whenever we do a test of the solar system, we look at this part of the parameter space. We look at pulsars. These are pulsars in orbit around each other, and I'll talk a little bit more about that in a second, the gravitational waves that they emit. In the 90s, early 2000s, we started doing tests of general relativity with cosmology, from the CMB and the expansion of the universe to structure formation in the future, hopefully LSST and Euclid. 5 years ago, we got into gravitational waves with LIGO and Virgo, with stellar mass black holes. A year and a half ago, we started seeing gravitational experiments with the orbits of stars, the S stars, around Sagittarius A star, both with gravity and with the UCLA observations with the Keck telescopes. And a few months ago, about a year ago, we started probing gravitational fields with M87, and up here is what would be with Sagittarius A star with the Event Horizon telescope. This is one of the reasons why we're looking at gravity in all of those places, because every different astrophysical setting that we're looking at looks at potential modifications in a completely different set of parameters, different potential, different curvature of the gravitational field. And of course, by definition, what we're looking at with the Event Horizon telescope is the near horizon region of supermassive black holes, something that we have never looked at before because we didn't have another experiment to help us do that accurately. That is not enough. Just saying where you're looking does not tell you everything you need to know about the test that you're doing. Here's another throw on a two-dimensional space for no particular reason of some of those tests. Expansion of the universe and cosmology on the left, orbital evolution of pulsars, gravitational waves with black holes, Sapir delay in pulsars, shadow solar system. Why did I throw them like that? Because some of those tests actually test what the gravitational field does in presence of matter, right? The universe expands, and how it expands, how the metric evolves, depends on the matter content. Other of them don't care about matter, are pure vacuum experiments. Some of them talk about stationary metrics. What happens in the black hole, in supermassive black hole, the metric doesn't change. It's like it's the asymptotic solution. it's independent of time. The metric around the sun doesn't change in time. Whereas other tests talk about dynamics. Again, the accelerated expansion of the universe is about the time dependence of the evolution of the metric of the universe. Gravitational waves with black holes is about the time dependence of two black holes orbiting and coalescing. So you can see that besides talking about what strength of gravitational field you're probing, one test, like for example, the black hole shadows, are probing the predictions of general relativity for vacuum and stationary metrics, whereas the expansion of the universe probes the predictions of general relativity for dynamical systems in the presence of matter. And again, it does not mean if I make a modification of gravity that it will modify both in the exact same way. This is one of the qualitative ways of thinking about that. And what we will be doing here is stationary metrics, vacuum of general relativity near supermassive black holes. But there's more to it. You really have to unpeel the onion of what is it that you're doing, what is the test that you're doing. And the next level of unpeeling that you need to do is all the different phenomena that general relativity predicts, even for one object. So let's take a simple spherically symmetric object. So this is as quantitative I'm going to be. This is the metric, right? It's mostly zeros. The diagonal is not zero, and one off diagonal term. And one of those terms describes the slowing down of clocks in gravitational fields. The fact that if you put a clock in a gravitation near the sun, it's going to tick slower than if you put it far away. It turns out that this part of the metric is what you probe, fun enough, not with a clock, but by measuring the precession of the orbit of Mercury. The other term of the metric is the warping of rods of space because of the presence of the gravitational field. Completely different phenomenon in some ways, and you actually probe it with different experiments. You probe it with, say, the deflection of light during solar eclipses, or the Sapiro delay that you measure when you measure the delay of signals from the Cassini spacecraft to us. There's that little r squared, which I'm not going to say anything about because this measures the dimensions of space. 2 is 3 dimensions of space minus 1, let's not worry about that. But then there's that off-diagonal term that measures the dragging of inertial frames. The fact when you have a spinning object, it actually drags all the inertial frames with it. And this is something that you probe by sending a satellite around in orbit around the Earth, like GraphProbe, or by looking at the motion of the moon around the Earth and the sun with lunar ranging. So what I'm trying to point out here is that even though we're talking about a single theory, there's so many ways to look at it. But more importantly, when you have a new experiment, you need to ask yourself, what of this did my new experiment measure? And more importantly, if I know what my experiment measured, did I learn something that I didn't know before? Did it make a quantitative constraint that I didn't have before? And of course, that requires that you make a quantitative measurement of potential modifications. It's not enough to say that this component of the metric is probed by the test. How well did it test general relativity? And how do you do that? You do that by parameterizing deviations. Again, this is really the only type of equation I'm going to show. There's a lot of mathematics behind. This is the Schwarzschild metric. Everybody knows, everybody likes. And it has particular quantities here, 2 here, 1 there, and you stick parameters in front of it, beta minus gamma. In general relativity, both parameters have a unique value. They're both 1, but you let them free. Because this is an expansion in the Newtonian in that potential, this particular type of approach is called the parametric post-Newtonian expansion. Then you have this metric, you calculate the predictions for a particular experiment. So for example, for the deflection of light, it depends, remember what I told you, only on one of those parameters. And then you use experiments, you measure the deflection of light or the Sapiro delay for that matter, and you put limits on that 1 plus gamma over 2 parameter. Eddington did it, not very well, to within 10% in 1919. And the limits have become smaller and smaller and smaller, with the best one today in the solar system on this parameter gamma with Cassini, the Sapir delay in the travel of radio waves from Cassini to the Earth to be about 1 part in 10 to the 5, 1 part in 100,000. So what one can tell, if you were to read about, for example, this test in the newspaper, you're going to hear general relativity passed another test with flying colors. If you were to ask somebody who does test of general relativity, what they would tell you is that in the solar system, fields of strength found in the solar system, when looking at stationary vacuum spacetimes, the RR component of the metric is consistent with the predictions of general relativity to 1 part in 10 to the 5. An extremely precise and focused answer of what is it exactly that we're doing with this particular test. So these are the kind of questions that we want to do, we want to ask, and we want to answer when we try to perform a new test of general relativity. Well, all this background work has not happened. And the one that we wanted to do with the Event Horizon Telescope is using the observations of this wonderful globe-wide millimeter wave interferometer, the Event Horizon Telescope that has telescopes from Hawaii in the west all the way to Spain and France now in the east, and from the South Pole all the way to Greenland, combined together in the 2017 observations. This is how the array looked in 2018 actually, but the observations are still from 2017, combined together to generate the first ever image of a black hole with horizon scale resolution. And what we found was this picture that I'm sure you've all seen before, which has a number of elements. I'm not going to go at all. I've given talks to several groups at the university here and other places about how we got to take that picture. What I would like to do now is how do we use this picture to learn something about general relativity. And the most striking feature of that picture is this big brightness depression in the center of the image. And this is the depression that we were looking for. And this is the depression that we identified with the shadow of the black hole. And the shadow of the black hole is surrounded by a narrow ring of emission at millimeter wavelengths. And this is something that we identified with the emission from the surrounding plasma. So we knew that we will be able to do something about general relativity with a black hole shadow because this is something that happens all the way at the horizon of the black hole. But to understand what we can do, we have to really understand what is that shadow and how does it probe general relativity. And back from the 70s, there were some early ideas of these black hole shadows. This is the time where everybody thought that accretion flows, accretion disks are very, very thin, geometrically thin, optically thin accretion disks. And Jean-Pierre Luminet actually did a numerical calculation that he then converted and painted everything by hand. This is a hand-painted output of the calculation that he got from his computer of what a black hole would look like if the black hole is accreting, as you see from the schematic, from a geometrically thin accretion disk. For the aficionados, these are the kind of Shakur and Shinyaev or Thorne and Novikov types of accretion disks. And indeed, as you would expect, any photon that comes close to the black hole gets absorbed by the black hole, and you have this depression, this weird shaped depression of brightness in the middle that looks quite different than the image that I showed you before. Even though this was the state of the art at the time, unfortunately, it was not very useful either in designing the Event Horizon Telescope nor interpreting the data. And the reason is that if this is exactly what was happening near M87, then you would have to do the observation in a wavelength that is impossible at about 30 nanometers, which is in the UV. The reason being that those geometrically thick accretion disks emit primarily thermal radiation, and the temperature of the thermal radiation near the horizon corresponds to a wavelength of about 30 nanometers. If this was the physics that was going on, we would never have been able, with current technology, to take the picture of the black hole. Thankfully, sometime in the 90s, what happened is that people realized that these geometrically thin accretion disks are not good descriptions of what happens near supermassive, low luminosity black holes. Instead, black holes accrete through a mode that is called the radiative increasing radiative inefficient accretion flows, or ADAFs, advection-dominated accretion flows. And those are very different settings. The accretion flow is very hot, so it's very puffed up and thick, but it's also very optically thin, which means that it does not emit in thermal radiation. Instead, what you see is you see emission primarily from synchrotron radiation of energetic electrons that are swirling around the magnetic fields in the accretion flow. And if you were to take the observation at about, say, a centimeter wavelength, then what you would see is you would see this puffed up fog, this puffed up atmosphere of that is slowly circling around the black hole, covering everything. The benefit of synchrotron emission is that it has a very strong dependence, its opacity has a very strong dependence on wavelength, which means that if I crank up the wavelength of emission, what will happen is that I will be able, the fog will become transparent, and I will be able to peer deeper and deeper and deeper closer towards the black hole. And this is a modern numerical simulation by C.K. Chan based on some early work that we had done with Ferry Aluzal and Ramesh Narayan. And the ending is something based on work done by Heino Falke, Fulvio Miglia, and Eric Agel here at the University of Arizona, actually. So this is what happens when I crank up the frequency, reduce the wavelength of observations. The synchrotron emission becomes optically thin, becomes transparent, and therefore I get to look straight into the accretion flow. And what I see is I see what we're expecting and what we found, a big depression in the middle with emission that is circling, of course, wobbling, of course, but is thinly surrounding this emission, this center of the black hole. And this depression in the middle is what we call the black hole shadow for these radiative inefficient accretion flows. But what does that tell us about general relativity? And to understand what is that really the outline of that black hole shadow, let me tell you quickly something about the Kerr metric. The Kerr metric has three characteristic radii. And here I plot them as a function of black hole spin from 0 to 1. The solid curves are when the black hole is moving together with the flow, and the dust curves is when the black hole is moving the other side with respect to the flow. The closest radius is the event horizon, the point of no return. We know all about that. The red curve is the innermost stable circular orbit. Matter slowly drifts inwards until it hits the ISCO. Inside that, there are no more stable circular orbits and matter just plunges. And that means that most of the emission in the accretion flow is actually coming from outside that ISCO. But then there's that blue curve here, the photon orbit, which is the place that if I were to shoot a photon perpendicular to its radius, the photon will make a perfect circle in a non-spinning black hole and come back forming a perfect orbit. And it turns out that this is an important quantity, an important radius that determines what the shadow is. Now, what I just told you about the perfect circle is true for a non-spinning black hole. If I take the black hole and spin it, then that inertial dragging frame that I talked about, inertial frame dragging term that I talked about, is going to make the orbit of that circle to precess extremely rapidly. And the orbits will remain at a constant distance, but they won't be circular anymore. We call those spherical orbits. The one on the left is for a black hole spinning at one spin frequency, the other is spinning at a different spin rate. And what you see is that photons never escape when they're put in that orbit. They stay at a constant radius, and the orbit precesses at an extremely high rate. Why is that orbit important? Let's look at it in a slightly different way. What I'm showing here is I'm looking down the black hole. The observer is all the way at the bottom, far away from the screen, like all the way down towards the floor. And there are three lines here. The red one is the horizon. The blue one is the photon orbit at 3 gravitational units. And the black line is a path of photons that reach the observer far away, the screen of the observer, but I trace them backwards towards the event horizon. Now, what I'm going to do is that I'm going to move the impact parameter, the path left and right, the path that these photons followed before they reach the observer. The one that I show right here is the photons that came straight down to where the black hole is. What if I let them move a little bit? I will freeze the movie for a second. I just want you to see this evolution. Hopefully it's not too choppy with zoom. But what you see is you see the effect of the extremely strong gravitational lensing around the black hole. So let me freeze it at 3 snapshots. The red snapshots is a bundle of photons that reads at that particular place in the screen. And when I trace them back, they got bent, they crossed the photon orbit radius, and they went straight into the event horizon, or they hadn't come out much from the event horizon. How much brightness did that bundle of photons bring me to my screen? Not too much, because there's not much optical path in the line of it. How about the green bundle of photons? This bent quite a lot, enormous gravitational lensing. There's a significant optical path. So if there is a lot of material and a lot of emission out here, I expect to see a lot of fluff, the accretion flow being there. But there's that critical impact parameter, that critical distance from the center of the black hole, that if I send backwards the photons, they come and become tangent to that photon orbit. And because the photon orbit is a circle, that bundle of photons spreads enormously. And now the brightness that I get here will be collected from all of those rays. Everything that is along those rays pointing towards tangential to those rays will line up and appear on that critical impact parameter. And of course, the same will be on the other side. So what do I expect to see in these big fat accretion flows where I do not have a photosphere, but I can see everywhere? Well, depending on how much material there is, how much matter there is, and what temperature they have, I expect to see a little bit of the fluff out here, depending on the wavelength that I was looking at, a big dispersion in the center, and this very bright narrow ring of emission at that critical impact parameter, such that if I were to trace the photons back, they actually become tangent to the photon orbit. This is the outline of the shadow, and that is exactly why we call the shadow the gravitationally lensed image of the photon orbit. So when we observe that big depression in the middle, we actually don't observe the horizon. The horizon is irrelevant. What we do observe, that depression, is the photon orbit. People always say, so why did you call your telescope the Event Horizon Telescope and not the Photon Orbit Telescope? Well, I think it's pretty obvious for a number of reasons why we call it the Event Horizon Telescope, but at the very least, we take observations with a resolution that is comparable to that of the event horizon. What we see is not the event horizon. So just to show you how it works when I throw a lot of material around the black hole, these are 3 GRMHT simulations, general relativistic magnetohydrodynamic simulations out of the Event Horizon Telescope, original set of the Event Horizon Telescope papers, and you see what I described. 3 different snapshots. You see the fluff, the accretion flow around. We pick the proper wavelengths of observation such that we don't see too much. We only see the innermost hotter parts of the hot electrons. You see this bright ring of emission around it. And of course, when you smooth everything out at the resolution of the detector of the telescope, then you cannot see this, all this finite details. What you see is the big depression in the middle and a narrow ring of emission around it. What is interesting is that, of course, when the ring of emission is very narrow, then it traces the outline of the shadow. And that's why we pick that particular wavelength, and this is what we see. But something else that you see here is that the image does not seem to care, first of all, about the plasma and the accretion physics, but also doesn't seem to care about the spin of the black hole. The one on the right is almost maximally spinning clockwise, or at the same, co-rotating with the accretion flow. The one in the center is not spinning at all. The one on the left is counter-spinning with respect to the accretion flow. And yet all images, there's a minor difference, but all images at the resolution of the detector appear more or less the same. How is that possible? Especially when I showed you that the radius of that photon orbit depends very strongly on spin. It went from 3 gravitational units to 1 gravitational units co-rotating and becomes much larger for the counter-rotating case. What happened? So I can forget again the the RMHD and the accretion flows and everything else. And I can just, since I know exactly what determines the boundary of the shadow, I can trace that boundary of the shadow just doing the gravitational experiment, the gravitational thought experiment. So if I have a non-rotating black hole, it's going to be a perfect circle. It has a particular radius, about 5 gravitational units. And look what happens when I spin the black hole up. Until I hit a really, really high value of spin, 0.95 or larger, the only thing that happens is that the shadow of the black hole just is displaced to one side. It's actually not pointing towards the center of the black hole, and keeps more or less a constant size and a constant shape, nearly circular shape. And this is something that happens, I don't have the time to go into detail here, but this is something that happens because of a very fortuitous cancellation between 2 different effects. I talked about frame dragging, and there's another effect called the quadrupole moment of the spacetime. When I spin off the black hole, one effect tries to make it oblate, as you would have expected from a spinning object. The other tries to make it oblate because it's about frame dragging, and the 2 practically cancel out. And what you're left at the end is that the characteristic radius, or multiplied by 2 the diameter of the black hole, is extremely weakly dependent on the spin of the black hole from 0 to maximum, and extremely weakly dependent on the inclination with respect to the spin from where you're observing it. And the difference is, you can do it, rough magnitude is 5 geometric units, give or take 4%. And this is really incredible, because what it tells you is that there's no free parameter in that gravitational test. If you know the mass a priori of the black hole, because everything scales with the mass of the black hole, then you can predict what that size of the shadow is. And it's either that in observations, or it's not. You have no wiggle room. You cannot say, oh, it's spinning. You cannot say, oh, I'm looking at a different orientation. Things that we usually have to worry about when we're dealing, for example, with orbits of binary stars and things like that. Neither the spin nor the orientation matters. So this is where we're going after. We have a parameter-free prediction of the Kerr metric. So how do we compare it with the data? Well, first thing that we do is we measure the diameter of that ring, and we can do it from the image, or we can do it directly through the data. I'm not going to go into details. But remember, we're using this ring as a proxy for the shadow. We're not measuring the shadow itself, we're measuring the bright emission that surrounds it. Where we chose the wavelength right, so the width of that bright emission is not very large, say 20%. So we cannot be biasing our measurement of the shadow more than about that. But of course, what we can do is we can also use a very large amount of the RMHD simulations, which we did, in order to calibrate. If this is the size of the shadow, the size of the ring that I measure, what is truly the size of the shadow that I get? And then I can predict. I can compare the size of the shadow that I measure to that predicted by the Kerr metric. Remember, there's only a 4% wiggle room because of the spin and the inclination that I don't know, but it doesn't matter. It's very small wiggle room. And the only thing that I need to know is the mass over distance to the black hole, but I know that a priori from gas or stellar dynamics, because I can do the gravitational experiment far away from the black hole, looking at the orbits of stars, and measure the mass of the black hole, or that quantity of its space-time far away. So for the case of M87, it turned out that we had 2 contradictory masses. One was from stellar dynamics, and when I plug that in, I get a predicted shadow diameter of about 40, give or take 40 microarc seconds. One from gas dynamics, which was a factor of 2 smaller. This discrepancy is actually quite common when in many other situations where we have both gas and stellar dynamics mass measurements. The gas dynamics are typically smaller, up to a factor of 2. And we think one of the reasons is that stars are honest test particles that are only affected by gravity. Gas dynamics, there are additional forces that affect them. For example, they can be pressure supported, and therefore the smaller orbital velocities that you measure, if you don't take into account of pressure support, you assign it to a smaller mass. But what we can do is that we can compare the a priori prediction for the shadow diameter to the measurement of the EHT. And these are different ways, directly to the images or from the fitting directly to the data. And the purple line is the measurement of the Event Horizon Telescope within the various uncertainties, the measurement uncertainties, as well as the uncertainty that has to do with the fact that we're measuring the bright proxy as opposed to the shadow itself. This is wonderful because it tells you that it is in great agreement to what one would have predicted using the stellar dynamics mass, which is the one that we gave the highest prior to. And in fact, you can ask yourself, what is the maximum or what is the probability for a deviation between those two? What are the chances that they're not the same? And it turns out that the predictions of the Kerr metric with a mass measured far away from stars, with a measurement of the black hole shadow from the EHT image, they're completely consistent with each other with a wiggle room of about 17% in size. Clearly, if we had picked the red line, the gas dynamics, we would have led to the conclusion that the Kerr metric is off by a factor of 2. We consider that to be very low prior for our measurements. We don't really expect to find such an incredible deviation from general relativity. So, and a priori, we had reasons to believe the stellar dynamics mass more. So we're going to focus on that 17%. So what the Event Horizon Telescope told us is that the predictions of general relativity of the Kerr metric are consistent with the measurement to within about 17%. And we call that the null hypothesis of general relativity, right? I made the hypothesis that general relativity is correct, and then I predicted what the shadow is going to be, and then I measured it. But the fact that the predictions and the observations match doesn't really tell me much about alternatives. It could have been that all of the other theories that I told you about in the very beginning also predict black hole shadows that are within 17% of the measurements. It also doesn't tell me what part of that theory actually determines the size of the shadow of a black hole. And as I showed in the beginning, there's many parts of the theory that one can in principle move. So to convert those measurements to a bona fide test of general relativity, there are a number of things that we need to ask. First of all, we need to come up with a parameterization, those betas and gammas that I told you before, that works near black holes. That was a good parameterization for solar system test, but it's not good at the strong gravitational fields of the black holes. Then we need to figure out what aspect of general relativity is it that we're testing really. We need to make an actual quantitative comparison to experimental measurements, figure out how much we can tweak those parameters. And at the end, of course, ask ourselves, did we learn something new? Are the new constraints that we put any different than what we had already done before? And this last part is what was reported in the physical review letters this morning. The problem, and that's something that we knew about 15 years ago, is that it's not easy to add those parameters to the Kerr metric. Because the minute you tweak your Kerr metric, the whole thing breaks down. And we actually had done a very systematic study. This is from one of the papers of my student, Tim Johansson, of various parametric deviations of the Kerr metric. The first 3 was what was known at the time. And we started finding things like, and there's a reason for that, like 2 time-like coordinates and 2 space-like coordinates, or time machines. You threw a photon into your space-time and it comes out before you actually threw it in. All sorts of weird things that tell you that something is wrong with the parameterizations you've done. So it took a lot of effort to actually find a way to tweak, to add parameters to the Kerr metric that allow you to go away from it, the kind of thing that we want to do a quantitative test of general relativity, without breaking it. And we figured it out. A number of groups figured it out, but with a big cost, a big penalty. And the penalty was complexity. So remember when I told you that little beta and gamma for the modification of the metric around the sun? This is the kind of things that you need to do. This is the work that I did again with Tim Johansson about a decade ago. This is the kind of hoops that you need to jump and the parameters that you need to define and how they need to be put in. And there's a machinery way how you do that in order to be able to deviate from the Kerr predictions, the Kerr metric, and still don't break it. This is our approach, and other people were equally successful, but not any less complex. This is a paper that appeared at the same time by Sarah Vigeland, Nico Yunis, and Leo Stein. They called it the modified gravity Bambi Kerr metric. And again, these are the modifications to the Kerr metric with a number of parameters. Of course, we can throw that metric, and we did it multiple times. We can throw that metric in a big computer and calculate shadows, right? That's not difficult. It's just computationally expensive. But good luck trying to figure out what aspect of this metric actually is that the one that determines the size of the shadow. And more importantly, good luck trying to figure out how to compare these parametric deviations with what we learned, for example, from the solar system. So we did what everybody else thought of doing, which is, okay, let's not worry yet about understanding it. Let's try to calculate those shadows with computers. So what we did is we took here on the left, the JP metric. This is work by another graduate student here in Arizona, Leah Medeiros. And we started changing the parameters, changing the spin of the black hole. And this is how those shadows move, changing one of these parameters. And what we found, to some surprise, is that the size of the shadow, again, doesn't seem to care that much about the spin of the black hole. So these are 5 different curves, one on top of the other, with different spins of the black holes, the size of the shadow as a function of one of the perturbation parameters. And it seems that fortuitous cancellation that I talked about in the Kerr metric seems to more or less survive in this particular parameterization. We thought, okay, maybe this is specific to the JP metric. How about we do it for the other one? And we found very similar results. Again, this one has a slightly bigger, but a weak dependence on the spin. But it turned out that in both cases, it was one type of parameter that always made the biggest effect in producing the size of the shadow. And very weak dependence on spin. And fun enough, that parameter, all those parameters primarily determined not the warping of the space, but actually the slowing down of clocks, what we called the TT, the time component of the metric. So this was actually where the breakthrough in the intuition came from, because we thought if that is the case, if with all these complex calculations, the only thing, the black hole spin doesn't make much of a difference, how about we throw away the spin, all the complications of the spin, and try to solve the problem analytically for a non-spinning black hole with all these modifications. And that was interesting. And then the other thing that we realized is that there was a very particular mathematical coordinate set, they're called the aerial coordinates, that actually simplify the problem incredibly from this extremely complex metric that I showed you before. And you can solve analytically for the radius of the photon orbit. And you can solve analytically for the radius of the shadow. And look what happened. Everything depends just on one parameter, one component of that metric. It depends only on that property of the space-time that tells you how clocks are slowing down as you get closer and closer to the black hole. It's actually kind of counterintuitive, even though Newtonian gravity is about the same, that even though what we're looking for is extreme gravitational lensing and warping of images, what determines that shadow is not the warping of space, but it's a slowing down of clocks. But having had this intuition, so what we ended up doing is we said, okay, now we're going to go one step further. Just as a proof of principle, not because we believe that this is a real situation, but just as a proof of principle. Let's take the full machinery again, all the bells and whistles of those metrics, and tune the parameters such that the terms that you can test with solar system, what we call the first post-Newtonian terms, are identical GR, something that you have never detected in the solar system. And I allow only things to be different when I go to second and higher post-Newtonian orders. So Minkowski, Newton, 0 first post-Newtonian, non-zero second post-Newtonian term. But now I have spins, I have all the other parameters, and then I can place constraints. So as a function of spin, this is again that one parameter in the TT component that matters. I can change the spin. It doesn't make much of a difference. The excluded regions are the grayscale. So this parameter has to be of order unity or like plus or minus 5, give or take, but not larger. And I can change the other parameters of the metric from -5 to +5, and they make extremely little difference, as expected based on the analytic calculation that we've done before. So just this tells you that even the current measurements of the shadow, this is the 17% limit, allows us to put a order unity constraint on a modification to general relativity that, as I will say in a second, I will show in a second, is completely inaccessible to solar system tests. In this particular case, it's at the second post-Newtonian order, but in principle, it can be at a higher order. Is it possible that this is because of the particular parameterization we've had, the JP metric? Well, we repeated it for the other metric, the MGBK metric. Again, Minkowski, Newton, no post-Newtonian, the second post-Newtonian, so the leading second post-Newtonian term, and we get something very similar. That parameter in that metric, it's constrained to be ±5, give or take. Spin has a very weak dependence, and this other parameter makes a very, very little difference. So the constraints depend very weakly on the black hole spin, and they depend very weakly on the particular parameterization of the deformations. And that's where we started realizing, and we believe that with all of those, both analytic and numerical examples, that we identified what is the key characteristic of the metric or of the predictions of general relativity that determines the black hole shadow. And we also demonstrated this way that we can make modifications to that key characteristic that would never have been seen in previous experiments. And yet we can place significant constraints with the Event Horizon Telescope. This is new information that we didn't have before. So why do I say that these are not accessible to solar system tests? Let me take one side remark and have a couple more slides after that. Of course, nobody believes that nobody thinks that all theories of gravities will be identical to GR up to first order and deviate beyond that. That was just a proof of principle. What you can do is you can write all the terms, like the first post-Newtonian, the second post-Newtonian, and so on, and solve the problem. And because we have one data point, the size of the shadow, for something that is nearly spherically symmetric, there's nothing else that you can measure. We can only place constraints in a long series of terms, in a sequence of terms. But what you see is that series very quickly converges. We were worried about that in the beginning because we're at the very strong gravitational field. But even after a third, even if you drop away the third term, the mistake that you're making is at the percent level. And our data, our current uncertainties are at the 17% level. So these terms are actually do not enter given our comparison, given our current uncertainties. So if that was the case, if you allow all of them, then you don't constrain one parameter at a time, but you constrain a linear computation of the first post-Newtonian and the second post-Newtonian parameter. Anything in that pink region or red region is excluded. Your theory better predicts something in the white region. But why did I say that those are new? This is new ideas. These are inaccessible to solar system tests. A couple of years ago, Cliff Will actually went through to quantify what one needs to do in order to measure those second post-Newtonian terms with the precession of Mercury. Now, why am I picking the precession of Mercury? It's because now we know that what we're testing is the time-time component of the metric. And among all the solar system tests, the only one that measures that tests the same component of the metric is the precession of Mercury. There is no way to compare what we've done with, for example, the solar eclipse measurements or the Shapiro delay measurements, because those measure something completely orthogonal. So what happens to Mercury? Well, if you have better and better data, you need to correct for a number of other effects. Classical precession because of solar oblateness, the frame dragging that I talked to you about, a post-Newtonian cross term, and something that's called the de Sitter precession. And after you correct all of that, you're left with that term that we can test, we can probe with a solar system, with a black hole shadows, but this is a few parts 10 to the -8 smaller than the first post-Newtonian term. Remember, the limit that we have on that parameter, that beta parameter, is 1 part in 10 to the 5. I need to to increase my accuracy by 3 orders of magnitude, about a factor of 500 actually, to be able to reach the same accuracy as the one that we attained with the black hole shadow with this particular parameterization. Precession is not something that you only see around the solar system. You can do it with pulsars, but the one that is even more exciting for us, because we're looking at the same black hole with the Event Horizon Telescope, is the precession of a star around Sagittarius A star. This is a wonderful work presented recently by the Gravity collaboration that actually detected the precession of the orbit of the S2 star during its nearest periapsis passage. And people have done this for tens of years. Measuring the precession does not constrain one or the other parameter, constrains a combination of them, just like what I showed you before with several of the other tests. And this is the result from the Gravity collaboration. The x-axis is the RR component, the y-axis is the time-time component, and the gray area is the part that is allowed. Everything outside the gray area is actually inconsistent with the predictions. Now, these are the first post-Newtonian corrections, just like what we do in the solar system. Again, to be able to reach the second post-Newtonian expansion, post-Newtonian terms like we can do, requires a factor of about 1,000 increase in accuracy. And that is unlikely that's going to happen in the near future. Last but not least, there's another wonderful gravitational experiment that probes general relativistic effects around black holes, and this is the LIGO-Virgo experiment. You've all seen the gravitational waves. They come, and as the two black holes get closer and closer together, the frequency of the gravitational waves increases. That means that the phases of the maxima of those gravitational waves actually evolve in time. It's not just multiples of the period changes, and one can write in general relativity a model, a post-Newtonian model, a parametric model for the evolution of the phase. And our friends from LIGO and Virgo have actually constrained the parameters of that post-Newtonian model. This red circle here is for the first post-Newtonian model. This is for the second post-Newtonian order. And because this is about the dynamics, you also have all the other orders that are completely not accessible to us, that we do as stationary metric tests. What you see is that this is, remember, the LIGO is at a very, very different curvature and mass scale than what we are. They're looking at stellar mass black holes. We're looking at supermassive black holes. In principle, they can be different results from the two of them. But what is interesting is that the two types, their results have also order unity constraints on possible deviations. And actually, if you forget the fact about the dynamics and ask yourself, what if I assign all these errors to the metrics of the black holes, then you can take those numbers and you can constrain them. You can convert them into upper limits and parameters like the ones that we're measuring, which are a factor of, say, half an order of magnitude smaller than what the Event Horizon Telescope does, but they're constraints of comparable magnitude. So I'm at the hour. I just want to cycle back to that plot that I showed you before, the landscape of general relativistic tests. When we wrote that paper 5 years ago, we had only a few of the tests possible. We knew about the solar system test, and I showed you about how one does those solar system tests. We knew about pulsar tests. Unfortunately, I didn't have time to talk about the wonderful general relativistic tests done with pulsar in this part of the parameter space. We started in the last decade collecting a lot of information to be able to do actual tests of general relativity with cosmology, and we'll only get better with things like LSST and Euclid. The last 5 years, LIGO, as I demonstrated again, provided order unity constraints in very strong gravitational fields of stellar mass black holes. A year ago, we started getting general relativistic tests using the S-stars around Sagittarius A star with the orbit by monitoring their orbits. And as of this morning, we have the first reported test of general relativity in a different place with the M87 image of the image of the black hole in M87 with the Event Horizon Telescope. And I just want to point out that all the tests on the right side of this figure have happened in the last 1 day to 10 years. And this is something that will only get better in the future. This is a wonderful time and place to be. Thank you very much.
Fantastic. Thank you very much, Dimitri, for the enlightening talk. And I encourage everyone to use their clap button and applaud. And we are going to open it up for questions. So raise your hands and I'll be looking out for raised hands. Sam.
Thanks. Can you hear me?
Yes.
Okay. So I have a fundamental issue with this approach to testing GR with this data. So you have a null hypothesis test and you have 3 assumptions.
Mm-hmm.
So you have an assumed mass for the dark central object. You have an assumed scaling relation between the mass and the observed emission ring, and you have GR. And
Mm-hmm.
so the null hypothesis test tests the weakest of its assumptions. So we can go through these and we can ask what is most likely to be wrong. So the mass, well, there's already a controversy about the mass, so that has some probability of being wrong. The scaling relation between the mass and the emission ring was derived last year in EHT paper 6 based on a suite of GRMHT simulations with various priors about jet physics. Exclude that model because it doesn't seem to have enough Poynting flex, which we believe is correlated with jet power, which there's a lot of astrophysics going into that scaling relation. So that could certainly fail if the astrophysics is wrong. And lastly, GR, which is one of the best tested theories, as you've pointed out. So I just don't see how this null hypothesis test can teach us anything about GR.
These are good points from naysayers, let me say, but I'm glad to address all of them. I'll go backwards. I think I spent the entire hour trying to convince you that general relativity has been tested wonderfully, but not when we're looking at, right? It is trivial to write a modification. I don't like it as much as anybody else, but it's really trivial to write a modification that gives order unit deviations around 1087 and it's completely hidden about anything else, right? So it is, there are many reasons why we like it, but there's many reasons to look for it. Now let's go to the other 2 assumptions. I agree with you that there is a scaling between the proxy, which is the bright ring of emission, and the size of the shadow. However, the calibration that we did actually does not care at all about it, really, because the maximum error that you can make is the width of that narrow ring, right? There is no way that you have, there are ways, but it won't be in any way of any high prior. There's no way to have an extremely narrow ring being, 45% outside the size of the shadow and being nice and narrow with a big depression in the middle. So yes, we did. And by the way, what you said about jets and this and that and the other, that was paper 5, by the way, and has nothing to do with the calibration. So the calibration.
You excluded certain models from that calibration based on jet priors. There's a table in paper 6.
No, it's in paper 5.
Did I share screen?
No, you should not. Sam, let me remind you that I was the project scientist when we were writing those papers. But point number 3, the masses. I completely agree with you. There are 2 different masses, and then you have to give yourself a prior, right? You can't say that I believe that it is the gas dynamics mass and therefore GR is off by a factor of 2. But there I will take your point of view to say that I don't expect a factor of 2 deviation in general relativity. I will pick the mass of the star. But where I think you will, give me 1 second, I stopped sharing, right? I just need to share another figure. What will remove one of those priors very quickly, I need to find again, oops, here we are. What will remove one of those priors extremely quickly is the next black hole, Sagittarius A star, right? And there, both because of the measurement of gravitational redshift and because of the measurement of the precession, we actually know M over D, which is the only free parameter that enters, to an accuracy of better than 1%. I usually joke that I know the mass of Sag A star better than my own weight, and especially these days of COVID. But that is completely removed from there because there's no doubt, because we're looked so close to where the, we're 1,000 Schwarzschild radii that will go away. If we're lucky and we find again a narrow ring of emission, so that puts an upper bound on how much the calibration can be off, then there's not much that you can do to go around it.
Okay, so I disagree, but I'd like to see that claim made in print, because as far as I know, the only claimed scaling relation is derived in EHT paper 6. It doesn't mention this narrow ring business, et cetera. I'd really like to understand the status of that as better.
Sure.
Okay, any other questions for Dimitrios? Well, if there are no other questions, I can ask one. So there are theories of gravity where the motion of matter doesn't, follow geodesics.
Mm-hmm.
Would it be possible, or the geodesic of the metric? So there are modifications, I should say, to the geodesic motion. So would it be possible that you can have matter actually just spoil part of this measurement, and because there's emission happening in areas where you wouldn't expect it from matter, and then thereby by not accounting for this, maybe your constraints are excluding certain types of theories of gravity, or is it the assumption that you're only focusing, for example, on metric theories of gravity right now? So I'm just trying to understand a little bit, what are the fundamental assumptions that go into this particular constraint?
True. So what we've done here, just like what you do in the solar system, you're focusing on metric theories of gravity, and you try to tweak the parameters to see how far you can go away from it. The fact that matter might not follow geodesics, I don't expect to make much of a difference, because again, we're using the location of the matter only as, say, a back illumination for the black hole to make that little ring of emission. So you can do the same by changing the dynamics of matter or temperature of matter and this and that. So for us, that is just something to illuminate the shadow. What will make a difference is whether photons follow the geodesics, because if photons, electromagnetic waves, do not follow geodesics, they couple, it's like a Lorentz violating theory, then of course this whole idea that you're going to have photon orbits and the photon orbits will be lensed in a particular way just goes out the window. I do not have a good generic parametric way of doing that. There are known, extensions of general relativity that allow violation of the Lorentz symmetry, and one by one, of course, you can always do it and calculate what the signature is. But what we did is practically identical to what all existing tests of metric theories does.
Okay, thanks. Any other questions for Dimitrios? Rachel?
Hi, it's actually Rachel. It's her roommate, Raphael Vieding, another grad student in the department. I had a question. So you talked a bit about how, the uncertainties in the mass play into it. What about uncertainties in the distance to the black hole? Does that enter into this at all, or what's the discussion there?
Very good. Actually, the only thing that matters is the ratio of mass to distance, because the mass scales the size of the horizon at the location of the black hole, and the distances just tells you what the opening angle, because we're measuring angles, we're not measuring actual physical distances. And it turns out that this is practically the identical degeneracy that you have in measuring the mass and the distance of the black hole with stellar dynamics. What you measure is not really the mass or the distance. Primarily, you measure the m/d ratio. The same is true for Sagittarius A star. And if you look here on the right, of course, this is infinitely better because we have really high quality data. But you see, you measure the, can everybody see the thing on the right? You still can see my screen, right?
Yeah.
Yeah. So what you see here is the mass of Sagittarius A star, the distance of Sagittarius A star, and there is a correlation along m/d. So you actually don't know the mass or the distance that as well, but you know the ratio of m/d, which is the only thing that matters much better.
Okay. In the chat, the statement from Rachel, which it was actually Raphael. It's a very helpful answer. Thank you.
Good.
So, okay, let's take one last question, Sam, and then we'll close.
I guess I didn't put my hand down. Sorry about that. I'm in Zoom novice.
Oh, okay, okay. All right. Okay, if there are no more questions, then, oh wait, there's another question in the chat. So could you please comment on how these results compare to the ones performed using X-ray data also on supermassive black holes?
Yes, so with X-rays, you do it in a slightly different way. You do it, especially for supermassive black holes, you focus primarily on the relativistically broadened profiles of lines, fluorescence lines, like for example, iron lines. And this is also an extremely powerful way of measuring the gravitational redshift at different radii from the black hole. The difficulty of those measurements, first of all, there's, we need better telescopes to do it, and there's planned X-ray telescopes that are focusing on this. But the difficulty with that measurement is that you really need to correct and you really need to understand what the astrophysics of that measurement is. You need to know where the emission is coming from. You need to know how it gets reflected. There's a degeneracy between the profile of the emissivity of the line and the space-time properties. This is something that we don't have to do with Event Horizon Telescope. The shadow is a completely gravitational achromatic effect. What will become better with the X-ray measurements is to be able to time resolve those lines, because again, the accretion flow is not going to be uniform and constant. It's going to be orbiting around and moving around, and being able to resolve those correlated differences between the Doppler shifts and the energies of the emission will be able to actually help you do like an orbital test, effectively be able to resolve away the astrophysics and be able to do a gravitational experiment. So hopefully high throughput, high timing future X-ray observatories will be able to do that.
Okay, so I guess we should all thank again Dimitrios for the wonderful talk. And by the way, I didn't pronounce your first name right in Greek. Right? I only pronounced the last name correct.
That is correct.
So yeah, let's all thank him again, and use your applaud button, and we'll see you next Thursday for the next Colloquium talk. Thanks again, Dimitri.
Thank you very much.